All right, here we go. This is Math 9, section 4.2, part 2. So Math 9, we are in Math Makes Sense textbook here. Pearson, Math Makes Sense 9. And yeah, we're going to take a look at section 4.2 today. So we did the first part of 4.2, examples 1 through 4 in a previous lesson, and today we pick it up at number 5. So let's read number 5 together here. A scuba diver goes underwater. The deeper he goes, the more water pressure he feels. Refer to the table here below to see the relationship between the depth and water pressure. So at 0 meters, the water pressure is 0 kPa. Now, you probably don't know what kPa is. This little k is from the metric system. That means kilo. And Pa is a unit of pressure named after a famous scientist a long time ago, Pascal. So this is kilopascals. And that's one of the common ways of measuring atmospheric pressure. Literally the weight of the air above you pressing down on you. Atmospheric pressure. Now, atmospheric pressure is very light. It's very small. It is small on top of a mountain because there's very little air above you. But down in the depth at sea level or somewhere down really low, there's going to be more. And under the water, even more. So so that was atmospheric pressure, kPa. Water pressure is even worse because it's, you know how heavy a bucket of water is, right? So imagine you're underwater. The deeper you go, the more pressure you feel in your ears, right? When you dive to the bottom of a deep pool or something, or you're diving in a lake. So that's water pressure. Literally, it's the weight of the water above you pressing down in on your body. So as the diver goes down 5 meters, the water pressure in kilopascals increases by 50. Okay, now we are going down, but this is a positive. So as the depth increases by 5 meters, we'll have to say it that way, the water pressure increases by 50 kilopascals. And we're going to write that in words here right now. Are you ready? So in words, fill this out in your notes. We're going to describe that. As the diver goes down 5 meters, the pressure increases by, and if we count that, we haven't really counted it yet, it's 5 meters every time here, and here it's 50 kilopascals. See that? It jumps, every time it jumps 50. So as the diver goes down 5 meters, the pressure increases by 50 meters. Okay? Or even better, for every 5 meters the diver goes down, the pressure increases by 50 meters. Okay? So that's good, and so is the other one I just mentioned. So as with an increase of depth of 5 meters, we have an increase of water pressure of 50. And I'll just show you here, right? This is plus 50 here, plus 50, plus 50, plus 50 each time. And this is plus 5, 5, and 5. You see that? So is this a linear relation? Yes, it is. Why? Because the pressure jumps the same amount every time. This is plus 50 every time. As well, the depth jumps the same amount each time. So there you go. That means it is linear. Okay, as a graph. Okay, let's look at, the graph is actually given to you over here. These are the points in the table. You see 0, 0, 5, 50, 10, 100, 15, 150, and 20, 200 right there. The points are just maybe a little off. I don't know, something's off. The little line's slightly off a bit. But since there are no negative values in the problem, we only need to concern ourselves with quadrant 1. And that will happen a lot of time in real life situations, right? If we're talking about time, if we're you know, as time goes by, you know, something happens and we can measure that. You know, usually there's a start time at 0. We can't go back in time, right? So no negative time, let's say. If we're traveling a distance, usually it's like before you start, you can't go back that way before you start. Like you start from a certain place and you move from there. So a lot of times it's going to be positive values on the x and positive on the y. So we only need to graph the first quadrant. Remember, this is quadrant 1 here of the 4 quadrants, right? So this is quadrant 1, this is quadrant 2, quadrant 3 down here, and quadrant 4 down here, right? So those are the quadrants. Okay, let's get back to it. So what depends on what? Okay, what is the dependent variable? And the dependent variable is the variable that's on the vertical axis, right? So water pressure. Water pressure depends upon the independent variable is the depth. That's what's on the x-axis. So it's the depth. And just in case you are having a tough time remembering, this is the dependent variable because it depends upon something else. So this is dependent. And this is the independent. It's kind of the one we start with when we consider our measurements. I'm going to start with the depth, and I'm going to measure the pressure. That seems most reasonable. Okay. All right. So notice on this graph as well, we used increments of 5. That's reasonable because, you know, the changes are 5 here, so that's not a bad idea. We used increments of 50 up here, and that's pretty reasonable too because each of these measurements go up by 50, so that seems very reasonable, doesn't it? There's also a title, and everything is labeled here. So the quantity that we're measuring and the units, very important that you put the unit symbols there as well. So the quantity and the unit symbol. So 25 what? Is it 25 kilometers, centimeters, inches? What? 25 meters. You have to put that on the label on the graph. Okay, so here's an important thing here. The points on this graph, the points that we've plotted in red, are connected with a solid line between them. And we don't do that always all the time. There's certain cases where we can connect the points and other cases where the points should remain separate. Now, why is this connected? Well, if you think about this, why this is connected, each point in between the points that we've actually graphed, I'll zoom in here and show you. So for example, I did not graph this point right here. And this is about 7.5 and 75. So is it reasonable to assume that that point exists? Well, if you go down 5 meters and you want to go down 10 meters, are you going to have to pass through 7.5? Yes. Does it make sense that there would be a gradual increase in pressure from 50 to 100 as you go deeper? Yes, it's going to happen gradually. So all of these points in between the ones that we plotted are reasonable for the situation. So that means you can go ahead and connect the points. This happens in time, in temperature, things like that, right? You can't just go from 5 below 0 to 50 below 0 without passing all of the temperatures in between, right? Even if it goes quick, you have to pass through all the temperatures in between. So if you are graphing temperature, you could connect all the dots of measurements that you take. That's reasonable. Now, one of the things that you wouldn't connect the dots maybe would be like somebody's favorite color. If you're talking about, you know, people, Jim, Peter, Susan, all that, and this is their favorite color, like here's green, here's red, here's blue. Well, okay, Jim's is green, whatever this person's name was red, this person was blue or whatever. Would you connect those dots? No, there's nothing in between there, okay? What's in between J and P, these two people? Well, nothing. What's the color in between green and red? Well, we could argue that, but they're separate data. So let's get back to the notes here. This makes sense to connect this data because the data is called continuous. It's continuous data. And like I mentioned, each point in between the ones that we plotted makes sense in this situation. So they could have their own points on the graph, so we would connect all the points, okay? It's continuous. All right. Now, as an equation, let's think about this as an equation, okay? Now, they help us out here by giving us some extra information, all right? And so let's use this extra information here. As the diver's depth is increased by 1 meter, the water pressure increases by 10. Now, if we look at the table of values here, we don't see 1 meter change and 10 meters change. But because we connected the points, I wonder if you could see this. Okay, here's 0, 0, and here's 5, 50. Now, if I put 1 in there, and 2, and 3, and 4 in between, do you see that if this goes up by 1 now instead of 5, this should go up by something less than 50. And as a matter of fact, it should go up by 1/5 of 50. So this is going to go to 10, 20, 30, and 40 in between. You see that? So these are the points that show up on the table, but really these points would work in there too. So let's again go from this information they gave us, and we're going to say that the pressure increases by 10. So 10, right? 10, that's this jump of 10 times, what is this? This is the depth, right? 10 times d, that's how we write this equation. 10 times d, let's start there. 10 times d for depth equals, what's this? Pressure, let's make that a p, equals p. And this is the way we've been building equations here for the last couple lessons. And then we might have to make some adjustment, right? Let's see if we do. Let's see if we do. So what's 10 times 1? Well, that's 10. So what kind of adjustment do we have to make, add or subtract, to get 10? Nothing, right? 1 times 10 is 10, so we don't have to add or subtract anything. So this is our equation, okay? That's our equation. Now, I want to take this opportunity, though, to show you that you did not need this information in between. You didn't need this, okay? I have showed you this, but this is really important. I want to show it to you again. You can build an equation here as long as this change is constant and this change is constant. This does not have to be 1 here in between. Most of the examples I give you have a change of 1 over here on the independent, but it doesn't have to be. So watch. What you could do is go this constant change of 50 divided by this constant change of 5 is multiplied by the depth, and that equals p. All right? So look at this. That's given the constant change on y up here and the constant change on x down here. Notice that this equals 10, p equals 10d. That's the equation that we got. So even from this graph, you do this jump divided by this jump, and that gives you your slope of the line. That gives you the rate of change, okay? So you can do that. That is excellent to do. You need to know that because we're going to be using that a little bit later, very soon. Okay? All right, moving on. Example 6. Suppose the following pattern is continued here of these figures. Describe the relationship between the shaded squares and the white squares. Okay, so for the first figure here, let's focus on this one. First figure, right here. The number of shaded squares is 1. The number of white squares is 1, 2, 3, 4, 5. Okay, everyone see that? 1 and 5. The second one, we have 2 shaded squares, and we have 1, 2, 3, 4, 5, 6, 7. All right. The next one, we have 3, and we have 1, 2, 3, 4, 5, 6, 9. Now, I actually didn't count that last one because I've seen the pattern. Do you guys see the pattern? Maybe you do already. Notice this initial situation right here, 1 to 5. Notice that we have that in this second figure as well. It's right there, you see? What have I added? I've added 1 more black shaded spot and 2 more white squares. So I guess 7 goes to 9. So again, 1 more black spot and 2 more shaded squares. And guess what? That happens again. So here's figure 2 plus 2 more whites and 1 more shaded. You see that? Here's the previous figure right here, plus 2 more whites and 1 more shaded. So that's where we build this pattern. And so 4 shaded is going to have 11 white. 5 shaded is going to have plus 2, 13. 6 is going to have 13 plus 2, 15. So let's just double check. 1, 2, 3, 4, 5, 6. Good. Has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 white squares. Look at that, perfect. And you can see that we have a consistent change in the, I guess this would be the dependent variable. Now, that's a little tricky to tell which one's which, I get it. But this one moves up by 1, so that's pretty typical that that's going to be, it doesn't always have to be that way, but that's going to be your independent variable. Notice that in a sense, we started with the shaded and we counted around it, right? To start with the shaded, count around it. So the shaded ones would be reasonably independent. Now, when the graphs, table of values are listed up sideways, it might be nice for you to, you'll have to know how to interpret this, okay? This is the independent. This would be like x, and this would be like y, okay? So we have the y value going 2, and as an equation here, this is what we're going to do. This is a consistent jump. So I'm going to go 2 times, and I'm going to make actually this one, should we make this like S or P? Probably. Let's go shaded and white, okay? Shaded and white. So 2, and remember, divided by this constant change, so that's 2 over 1. 2 over 1 times S equals W. That's where we start. And then, of course, we have to test some points to see if there's any adjustments we have to make with a plus or minus anything over here. So 2 over 1 we can just rewrite as 2. That's great. So does 2 times 1, does that equal 5? No, it doesn't. 2 times 1 is 2. So what adjustment would we have to make to get to 5? We'd have to add 3. Oh my. Disappear. There's MrMathWell.com if you want to go there and find this video. Okay. Thank you, computer, for crashing on me. So 2 over 1 times S, which we're going to just write that as 2. And then the adjustment we would have to make would be have to add 3. 2 times 1 plus 3 to get 5. So let's test this out and see if this is a complete equation. Let's test this one. 2 times 3 is 6 plus 3. Does that equal 9? Yeah, 6 plus 3 equals 9. And what about this one? 2 times 5 is 10 plus 3 equals, look at that, 13. So this equation is perfect for this situation. That's how you build your equation, okay? All right, so since I don't have a class actually here, I'm not taking questions right now. So if you have questions, hopefully you'll ask your teacher in class or ask me when you see me. Let's do second page here. All right. I might go just a little bit quicker here so we can get done this lesson in reasonable time. So this one here, since there's no negatives, this value, we're only going to concern with pattern 1. Oh, this is the graph of what we've just been encountering there. So the white squares, right? White depends on the shaded. We started with the shaded and we counted the whites. Okay, excellent. So we use increments of 1 on the x-axis there, and increments of 3 on the y-axis. That would be a great scale to use. We've labeled everything, great. Now, I am not going to draw a line between these points, okay? And why is that? Well, it's because we're dealing only with whole squares here. So we can't have a fraction of a square. So how many shaded squares? We can't have 1.79 shaded squares, right? It's only 1 shaded square, and then it jumps to 2, and then it jumps to 3, and then it jumps to 4. So we would not connect the points. Even though this is linear, the dots seem to line up. It's a linear relation, but we would not connect the dots on the graph. And that's because we call this data discrete data. Discrete means separate, okay? Discrete. So these points are not connected. Okay, we're not going to start point 4.1 sine. We're going to keep going with this lesson here. All right, from the equation, find the missing variable. Are you ready? Use the linear equation, or relation here, which is an equation really, y equals 2x plus 5, to find out what the y value is, so we don't know what the y is, when x equals 3. So in doing this, we want to substitute x equals 3 into the equation and then solve for the unknown y, which is going to be really easy. Watch this. I leave everything alone, but it replace x with 3. And 2x means 2 times x, so that's going to be 2 times 3. See that? So now I just evaluate this side. Y equals 6 plus 5. Y equals 11. Good with that? I hope so. Okay. What about, let's do B. What's the value of x if y is 25? Okay, so now what I got to do is I got to do 25 in place of the y here equals 2 times, I don't know what x is, plus 5. A couple ways you could look at this. This is pretty easy to do. You could do a lot of this in your head actually, right? If this side is 25, this side also has to be 25. If you have 5 right here, that means that 2x has to be 20. So 2 times what gives you 20? The answer is 10. But if that's too much for you to think about in your head at once, which I understand, then let me show you how to solve an equation. Now you've seen this before. You might be a little out of practice though. So I am going to try and get x all by itself to solve for x. So I have to take away 5 here from both sides to get rid of or to eliminate this plus 5 on this side. So this is going to be 25 minus 5 is 20 on this side. And these 5s are gone, so it's just 2x on this side. All right, we're getting close. Now I further isolate x by taking this 2 away. And again, this is a 2 multiplied by x, so I'm going to divide by 2. And that's going to give me, on this left side, 10 equals x. So x equals 10 is your answer for B. Okay. All right, I hope this is making sense here. I hope this is going well for you. Let's consider C here now. So when x is 3, y is 11, what does this mean? Well, okay, so what does that mean? That means that we have a pair of values for x and y that satisfy this equation. Okay? So when x is 3, y equals 11. If you think about it in terms of a graph, there is a point that has a x value of 3 and a y value of 11 that is on the graph of this equation. So point 3, 11 is on the graph of this y equals 2x plus 5. That's what that means. And also, that's graphically, you think about it visually. Algebraically, or just thinking about the numbers, these are the pairs of numbers, x and y, that make this equation absolutely true. Okay? If you have a different set of numbers and the equation is not true, then that point would not be on the graph. Okay? So D, if we look over here, if x is 20, y is 25 and x is 10, what does this mean? Well, we could also say the point x value 10, comma, y value of 25 is on the graph, okay, also of y equals 2x plus 5. And those are the values for x and y that satisfy the equation. Satisfy, that's the terminology that you'll hear, satisfy the equation, okay. All right, I'm going to get you to do these two questions here. What's the value of x if y is 23? And what's the value of y if x is negative 2? So go ahead and take a couple minutes and work on that right now and see if you can get those answers, and I'll show you what those answers are in just a second. All right, hopefully you tried that, and let's take a look. So here's our original equation, y equals 3x minus 4, and I've substituted y equals 23 right here. I want to get x by itself, so I'm going to add 4 to both sides. Add 4. 23 and 4 is 27 equals 3x. I'm going to divide both sides now by 3, and I get 9 equals x. You can flip that around and say x equals 9. There's your answer. Over here, this one's easy. You don't have to move any terms around at all. You just put x in, and guess what? Y is already isolated by itself. So you just evaluate this side, and you should get y equals negative 5 over here. All right? Hope that is making sense. We have one more page to get through, so let's go ahead to the last page here of 4.2. All right, for each of the following tables, find the missing values. Okay, well, this is kind of interesting. We should know that there are some patterns we're looking for. Okay, now the pattern here is +1, and so on, right? +1 each time. So this pattern should be the same as well. We're talking about linear relations. And the only one that I can test is the jump between 22 and 31. So what is that? 22 plus, is that plus 9? Plus 9 is 31. So guess what? I need to add 9 to 4 as well and get 13. Does 13 plus 9 give me 22? Yeah, that works. So what's 31 plus 9? That should be 40. Okay, so 13 and 40 are your missing values there. Okay, I'm going to let you do 2 and 3 on your own. Give that a try, and then I'll show you the answers here in a moment. So try your hand at 2 and 3. All right, here are the answers for 2 and 3. Check to see if you agree. I've got, I noticed that we add 6 to each one on the y value. So I add 14 plus 6 is 20. 20 plus 6 is 26. Over here, I've got multiple spaces missing, but I did notice that between -9 and -8, I would have to add 1 there. So I'm going to add 1 to -8, add 1 to the -7, so those are the two values there. And I noticed that the separation between the two numbers given in the x column would be +1. So 3 plus 1 would be 4, plus 1 is 5, plus 1 is 6, plus 1 would be 7. Okay, so those should be your answers for 2 and 3. All right, let's work at, this is the last thing we'll do here, let's work at getting information from the graph. Okay, so from the graph, let's find missing values. So we did this just now from the equation. Let's do it from the graph. And we're going to spend a lot of time in a later section, I think 4.5, we're going to talk about this quite a bit. All right, this is going to be the focus of the lesson for 4.5, but let's just see if we can figure something out here before then. So what's the profit for working 2.5 hours? So obviously you see hours down here. Profit is how much money you would make by working that long. So 2.5 hours on the x-axis would put us right about here. See? There's 2.5. So what you do is you find out what the graph is telling you. Well, at 2.5, if you follow this all the way up until it touches the graph, this is a point that looks like it would be on the graph. You see how it's right in between those 2 points? And so what is the y coordinate for this exact point? And we just go over to the to the y-axis, and we find out what number would be right in between 16 and 24. Well, that's a difference of 8, so if we add 4 to 16, it looks like we should get 20. So the profit for 2.5 hours should be 20, and there's no units there. You should put units there, dollars. So it would be $20, looks like. Okay? So again, that's using the graph instead of the equation to get this information. I think we've mentioned this before, but maybe not. This might be the first time we've talked about this. Interpolating. This is what we call getting information from a graph or even from a table of values in between points that we've already know are true. So those points are the ones that we know for sure are true. And if we want to get information in between those points, that's a process called interpolating. So inter means in between, inter. Okay, interleague play. That's two leagues from teams from different leagues playing each other, or inter-school play. Right? When we play basketball or volleyball or whatever against another school, that's inter-school play, in between. All right, here's the next question. What is the profit for working 6 hours? Okay, very similar question. But 6 hours would be over here on the x-axis. And notice, please, that there is no graph up here. See, there's no graph at all. So how do we do that? Well, again, math is about recognizing and using patterns. So the pattern is, it looks like, as we've mentioned before, that every hour of work, it looks like the pay goes up by $8. So you get $8 an hour, it looks like, in this paying job. And so another point should be here. You see? If you go up from 5, you should go up another $8 from 40. So guess what? This should be 48. And when you extend the graph, when you do this, you should put dotted lines like that, okay, in either direction. So it looks like if this pattern were continued, 6 hours should give us $48. So that's what we put. Profit of $48. Now, this process is called extrapolating. Extra. Think about extra. That is outside of or beyond, right? Extra. You have extra work. It's beyond your normal work. You have extra recess time. Well, that's time that's beyond what you normally get. It's extra. It's outside of. So extrapolating, similar to interpolating, it's called extrapolating. That is to gain information from a graph that lies beyond the plotted points that we know for sure. We're extending that pattern. Okay? Lies beyond. So interpolating is between, extrapolating is getting information from beyond the graph that's shown. All right, great. I'll give you your 4.2 assignment as we conclude. Okay, if you're in my class here, this is the assignment I'm giving you. Your teacher may have a different assignment for you, but anyways, yeah, I hope that you get lots of practice here and you have good success with this chapter. So again, this was section 4.2, and the title was, and this is the second part of this title, the title was just simply linear relations. What can we learn about linear relations? So 4.2.